Hello everyone, welcome back to Explaining Physics Concepts, and today we are looking at episode 3, Simple Harmonic Motion, part 1. And in this video we will be focusing on only three things: what is SHM, a few formulas, and the energies in SHM. So I've broken it down, and everything that I'll tell will be covered in the syllabus as well. So starting off with what is SHM, I'll write a definition, and once I've written that, then I'll explain what I mean. So SHM, the displacement from a fixed point is directly proportional to acceleration from a fixed point but in opposite direction. Okay, so SHM, if anytime you see a object doing this, you should know that it's carrying out simple harmonic motion, that is to say, we know what displacement is. So if I were to draw this diagram, there's a diagram that I'm going to draw, and that is going to help you in every step of this chapter. So if I were to draw this, okay, I have a pendulum here, and if I start moving this pendulum, it's going to perform simple harmonic motion in a way that it's going to go here, so this is like the motion that it's going to carry. It's going to go here, and then it's going to go here. Now there are a few things that we need to know. This is where it's in equilibrium. And this is where it has reached its maximum height, and whenever you have maximum height, that is amplitude. So I will say it has reached its amplitude. So you're starting here, you're starting slow at equilibrium, and then you move all the way here. So there's amplitude here as well, because it had reached its maximum. Now in equilibrium, when it's not in equilibrium, we have to see what happens to its displacement, we have to see what happens to its acceleration, and we have to see what happens to its velocity, kinetic energy, gravitational potential energy, all of that. At this point, it has maximum velocity, because you must have heard how whenever something reaches its maximum height, the velocity there, it gets zero. We have done that in simple, in the beginning of chapters of in O level as well, that whenever we have an object and you throw it all the way up, and when it reaches its maximum height, the velocity, it always gets zero. So if velocity is maximum, and so that means that its displacement is zero. So they have like an opposite relation, whatever happens. So when it reaches maximum displacement, you will see here where it reaches maximum displacement, because it has reached its maximum height, there the velocity will get zero. Simple. And now what makes it even easier is that when velocity is maximum, obviously the kinetic energy will be maximum. And when this is zero, the gravitational potential energy will be minimum. And here the acceleration will be zero as well. Why? Because we just said here the displacement from a fixed point, we have written the displacement from a fixed point is directly proportional to acceleration. That means whatever happens to acceleration will happen to displacement. This was just the first part. I'll explain this opposite direction part in a while. So we have said whatever happens to the displacement when acceleration, when x is 0, displacement is 0, the acceleration will also be 0. And here goes the same. When displacement is maximum, acceleration will be maximum. And since this is maximum, gravitational potential energy will be maximum, and kinetic energy again will be minimum. So you can see whatever happens to displacement will happen to acceleration and gravitational. Whatever happens to the displacement, the opposite will happen to the velocity, and the velocity and kinetic energy, both of them are related. So this is extremely important. Now, what do we mean by in opposite direction? That is to say, they are proportional together, however they are acting in opposite directions. If this is acceleration, this will be displacement. They're going to be proportional to each other, but they will be going in opposite direction. Now, let me explain this through formulas as well. We have 3 formulas, and in my previous video I've also explained how whenever you have to go from one thing to another, you differentiate it by t. That is to say, if I have to go from displacement to velocity, I differentiate it by t. Velocity to acceleration, again I differentiate it by t. So our starting formula is x is equals to x naught sine omega t. X naught here is my amplitude. X is equal to x naught sine omega t. Now, if I have to go to the velocity now, I have to differentiate it by t. And when I differentiate it by t, I get v omega x naught cos omega t. And then again, if I differentiate it by t, I will get acceleration minus omega square x naught sine omega t. You can see how you're just adding on omega, you get omega, and then you get omega square, and then sine, cos, sine. And this negative sign again tells us of what we just talked about, that they are proportional to each other, but they are in opposite directions. Acceleration, and then you have negative sign, which shows opposite direction, right? And if I were to even graph this to help you better understand, if I were to look at the acceleration, it's x against t, and here is our amplitude x naught. And since you know this is a sine graph, you know how sine graphs are made in math, so you start from 0 like this. This is how you form a sine graph, and this is negative amplitude, because again it's going to go up and then it's going to go down. This is what oscillation is. It's going to come here, then it's going to come here, so there will be amplitude in both directions. And then if I were to draw for the velocity, this is velocity and this is t here. Now, how do cos graphs start? They start like this, and then this, and then this. And now for the acceleration one. You must be thinking that it will be like this. No. There is a negative sign here, so you're just going to invert this entire sine graph and form this. So you got acceleration, velocity, and displacement, right? And now I hope this was clear. You have to look at what sign cos, you know how sign cos graphs are made, and here since you have a negative sign, you're just going to invert this sign graph and form this sign graph. Now you have to keep this entire image extremely important. Oh my God, I don't know how that works. Never mind. Okay, now I'm going to make 2 more graphs, and that will help explain the definition even better. And that is acceleration against displacement. Now we know acceleration and displacement, they are directly proportional, and whenever there is a directly proportional graph, it is always a straight line through the origin. So I'll draw a straight line through the origin. Now a straight line through origin can be like this, or it can be like this. I'm going to go for this one. Okay, let me just make it better. It will be a straight line through the origin. Straight line through the origin, and in this direction, not in this direction. Why? Because this is a negative gradient. This is a negative gradient. Number one, they are directly proportional. They usually even ask in questions, explain how this shows that this is a simple harmonic motion. Reason why is, number one, because there is a straight line going through origin, which shows that it is directly proportional. Number two, it has a negative gradient, which show that they are acceleration and displacement are in opposite direction. You can see when displacement here is positive, this is negative, and when this is negative, this is positive. So they are in opposite direction. That is why we chose this. If I were to go for this line, when displacement is positive, acceleration also positive, that wouldn't have resulted in them going in opposite direction. That is why we had to go with this line. Another graph I will draw here is velocity against displacement, and the graph of this is going to be quite interesting, and let me tell you how. Let's just draw the main points. If I were to go back to this figure here, we could see that velocity and displacement, they have opposite direction. When velocity is maximum, displacement is 0. When displacement is maximum, velocity is 0. We're going to just do the same here. Here, at this point, at an amplitude, when we have the amplitude, the velocity is going to be 0. And here, when we're going to have maximum velocity, the displacement is going to be 0. And the same goes here, and the same goes here. And you can see this forms a circle. It forms a circle because I told you that the diagram that I've made above is extremely important, and it shows that velocity and displacement have a literally opposite relation. Whatever happens to velocity, the opposite. Here the velocity is maximum, but the displacement is 0. Here, let's say we have displacement 2, the velocity will be 0. Here, let's say we have velocity of 2 and displacement is 0, 0, 2. So you see, and the same will be but in opposite direction. And the reason why it's going in opposite direction is because it's a vector quantity, and we're taking into consideration the negative signs. This we're done with what is SHM, we're done with formulas, and we've looked at their graphs as well. The last thing we're left with is energies in SHM. Now, what do we mean by energies in SHM? Before I move on, there is one formula that I would like to write here, that is velocity is plus minus omega x naught square minus x square. Now, we have this velocity formula, and there was one we wrote above, omega x naught cos omega t, which I wrote up of. You can only use this formula when t is not given. So you can go for this formula. The reason why I've written this is because it's a vector quantity. So it can be positive, it can be negative. Now we're going to move on towards energies. Energies, just three energies. You have total, kinetic, and gravitational. So let's start off with kinetic energy. Kinetic energy is 1 by 2 mv square, a formula that we all know. But what do we write in v? We're going to write this one and not this one. We're going to go with this one because t isn't given here. So I'm just going to replace 1 by 2 m omega x naught square minus x. So you can remove the plus minus because it's just to show that it can be positive or negative. And then when you take square, you get 1 by 2 m omega square x naught square minus x square. I hope you know x naught square is the amplitude and x square is the displacement. Amplitude is the maximum displacement that it travels. And again, we have the gravitational potential energy, and that gravitational potential energy is simply going to be 1 by 2 m omega square x naught. 1 by 2 m omega square x square. Now, what do we know about total energy? Total energy is kinetic energy plus gravitational potential energy. 1 by 2 m omega square x naught square minus x square. The reason, if you're wondering how we derived this, at equilibrium, the only thing that we have omitted from this formula is x naught square, and x naught square is the amplitude, and we know that you have maximum gravitational potential energy at the amplitude, and so we have 1 by 2 m omega square x naught because we're saying when amplitude is not there. Maximum displacement, we have the maximum displacement, and that is maximum displacement is the amplitude, so we have written 1 by 2 m omega square x square. And then when you add these two, you get 1 by 2 m omega square x naught square. Now that we are done with this is the kinetic energy formula. There is one graph that depicts all of this as well. Okay, here we have x, the displacement. Here this is the energy, and let's just go with, okay, here I can assume we have the amplitude. Now, when we have maximum amplitude, at maximum amplitude, this is maximum amplitude. What is zero? Which energy is zero? At maximum amplitude, the velocity is zero, so kinetic energy is zero. So here, kinetic energy is zero, and here the same as kinetic energy is zero. But when amplitude is zero here, which energy is maximum? Kinetic energy. So you can see it forms a dome like this. It has to be of the equal length. It's just not right now, but it has to be equal. And kinetic energy. Now, when there is maximum amplitude, there is one energy that is maximum as well, that is gravitational potential energy. And when amplitude is 0, the gravitational potential energy is also 0. Amplitude is 0, which means it's an equilibrium. So when it's in equilibrium, gravitational potential energy is maximum. So you can see it forms a U shape too. Like this. It has to join this. And in the middle of this all is our total energy. And the total energy, it remains constant throughout. So this is our total energy. This is our gravitational potential energy. And this was the graph representing all of these, and it becomes very easy if you understand what happens in equilibrium and what happens in equilibrium and in amplitude. And I hope all of this made sense, and thank you